Hello everyone, I'm Shashank Jenke, and in this video I'll be walking through some of the key concepts that we explored in our Spring 2025 Data Science course. So over here we can see that the evidence lower bound ELBO in variational autoencoders and diffusion models. And in VAE, ELBO helps us in approximating the intangible log likelihood of the data, and it has two parts. The first is the expected log likelihood or reconstruction loss. It's shows that like how well the model can be rebuilt for the input, and for the second it's like a KL divergence, which ensures that the learning latent space stays close to the normal distribution, and mathematically we can see over here. And now the diffusion models are also used the similar principles, and they add noise to the data in forward process and then learn to revise it. The ELBO is derived from the log likelihood of the clean data and is often minimized through denoising laws, like the difference between the real and the predicted noise. And over here, like in the standard VAE, the objective balances between the two parts, like how well the model reconstructs itself and the input, and how close the learned latent distribution is to the standard normal distribution and all. The β-VAE changes this by multiplying the KL divergence term with the beta. When the beta is greater than 1, the model solely focuses more on regularizing the latent spaces, which often leads to more disentanglement. And yeah, but this can be reduced by the quality of reconstruction. But when the beta is 1, it behaves like a normal VAE. So like by adjusting the beta, we can tune the model based on our goal, like either the better reconstructors or the more structured latent features and all. This makes the beta VAE a more powerful tool in representing the learning. So in the diffusion models are generative models that create new data by simulating the two-step process, the forward diffusion and the reverse denoising. And in the forward process, we slowly add the Gaussian noise to the real data over many steps, and it becomes a pure noise. And when it comes to the reverse process, like this is where the model learns to remove the noise step by step. Like it gradually it recovers its original structure, and then we train the neural networks to predict the model and to remove any added noises using loss convention that compares with the predicted noise and to the true noise. So like in short, the diffusion model learns how to turn the data into a noise and then how to reverse it, and it also helps us in generating a new data by denoising noises and all. So in the Gaussian VAE, the loss function is derived from the ELBO, evidence lower bound, and it has two main components, the reconstruction loss and the KL divergence. The reconstruction loss is measured by it's a loss measure how well the decoder can create the original input from the latent space, usually using squared error or the binary cross entropy. And the KL divergence acts as a regularizer, pushing the learned latent distribution to a closed standard normal distribution together. And they ensure that the model is not only reconstructed, but it also has a meaningful and continuous learning in the latent space. And yeah, so in the VAE, we need to sample some random stuff like some latent variables, but normal sampling needs some backdrop. The representation trick fixes that by rewriting the sample as mean plus some noise standard deviation. That way, the randomness separates between the mean and the variance. And during our course, we learned and we looked on several foundational and papers. Like some of the papers which motivated me more is this one, improvised techniques for training GANs and by sampling. This paper presented the techniques like feature matching, min batch discrimination, and virtual batch normalization in order to stabilize the training. And in this paper, we the professor introduced the LabGen architecture, which uses multi-scale coarse to fine generation process. and this approach is demonstrated superior visual quality compared to the earlier GANs. And over here we've listed some of the papers which are discussed by the professor. And the auto-encoding variational bias by Kigma and Welling, it explained how to optimize the ELBO by using the reparameterization trick, enabling the efficient and interface and learning. So the importance of GAN, GAN taught me how AI can create realistic images by training on new networks. VAE taught me how deep learning can combine the comparison and the creativity through the probability encoding. Diffusion models showed me how to to remove the noise and to generate high quality content like images and all. And by using these, I have built small projects like generating images with the diffusion and training some sample VAE. Like for the future use, I would like to use these models in practical applications like image generating, data augmentation, and text-based insights. That's all from my side, and thank you so much for listening.